The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, welcome back for the last hour in this course. We've discussed all kinds of things about lasers. Certainly not everything. I haven't touched on Q switching, cavity dumping, and techniques for mode locking, and so on. But I think, I hope, if you didn't have too much of a background, now at least you can see that there's nothing that magical about lasers. That they all make sense. And if you were on some desert island with a bag of tricks, you could probably create a laser for yourself. Now, as I mentioned earlier, I want to change topics now. I want to switch to fiber optics, because fiber optics is playing a key role in our lives today, and I think it's good for all sorts of people to know how fiber optics, how it works, how it works, and some of the developments have been going on in fiber optics, and maybe a few words about some applications of fiber optics. So here is the very short course on basics of fiber optics. So the first question one asks, well, what's a fiber? All right. Now, fibers have been developed for many years, way before lasers, and they basically look like this. If you look from the end, they look like have a core, you see, which is one type of glass, and of certain index, let's say index N1, and surrounded by another glass of index N2 called the cladding. And then the cladding is surrounded by a jacket, and depends on the type of material that you use, but whatever, the jacket then protects the cladding. The index, the refractive index N1 of the core is bigger than N2. Sometimes N2, the cladding material is just plain silicon dioxide, and the index, the material in the core is silicon dioxide plus some impurity with germanium dioxide to raise the index. So the question is, what's going on in here? Why play with all these indices? So the key thing here is a total internal reflection. All right, the propagation of light in fibers based on total internal reflection. So let's then review it. Here's a ray of light hitting the surface, the interface here between N1 and N2, between the core and the cladding. If this incidence angle is bigger than the critical angle, then the light will be reflected and bounce around until it comes out the other end. And because just like going from glass to air, and the critical angle is given, as we remember from high school, as sine to the -1 of N2 over N1, where N2 is the smaller index and N1 is the bigger one. If this angle of incidence is smaller than theta critical, then there will be some transmission of light, and not all the light will be reflected. Just to remind you some more of what's going on, let me remind you of the perfect mirror. When you have a perfect mirror, the light comes in, and essentially close to 100% of the light gets reflected, and the reflectivity is close to 100%, as I say, is 1 as a function of angle of incidence. But if you have, again, the glass-air interface now, we're coming from the glass side, then as we vary this angle, the angle of incidence, then the reflectivity of this interface then depends on the polarization. But right now we're not going to get involved with polarization, but basically starts, let's say, between glass air, starts at like 4%, and for one polarization goes through 0, which is the Brewster angle here, and then rises at the theta critical to 100%. And for the other polarization, then it doesn't quite go to 0, but again still rises and goes to 100% at the theta critical. So it doesn't matter which polarization, both polarization will go to 100% for theta critical and beyond. And that's what we take advantage of in fibers. And let me tell you, this is really 100%, because you wouldn't get such low loss fibers if this weren't. Now, the other interesting thing that I want to point out, again from high school stuff, is that there is what we call evanescent wave here. There's a field that propagates in the vacuum or in the air here, but essentially just goes in and comes back again. It's not a loss. It's just that when you have a glass-air interface, there is a field that does penetrate, but it's still not considered as a loss. But then comes back here and gives us 100%. While in a perfect reflector, there is no field present on the other side because the light, 100% of the light gets reflected at the interface. Okay, so if you keep that in mind, that there is an evanescent field, there's a field penetration into the lower index medium, the smaller index medium, in this case it's air. All right, so with this as background, now let's look at the propagation in a fiber. Now, it's not like I showed you here, exactly like I showed you, is the ray approximation. But basically, when you do the calculations, what you get is a mode, essentially, just like the one in lasers, is a field distribution here, where that peaks at the center of the core, and also extends a little bit into the evanescent field. This is the evanescent field, extends into the cladding. So you can see this is the size of the core, but you see the orange, this orange, if you can see it as orange, it basically extends beyond the size of the core, and that's what we call single mode propagation. Okay, here's the field distribution, here's the side of the mode. So it extends a little bit into the cladding. Most of it, let's say, goes into the core, part of it goes into the cladding, and propagates right down the fiber. I mean, this ray idea is fine for explanation, but basically, when you do the calculation, proper calculation, that's what you get. You get this for the lowest order mode. Now, how does the light look like when it comes out? Then basically, let's go back to the ray picture. Where the ray picture, remember we said that the angle has to here be either equal to the critical or bigger, and then that determines the acceptance angle going in, because rays of light coming in outside this cone here will not undergo total internal reflection, complete total internal reflection, and will be in trouble because they won't propagate for too far and they'll be attenuated. Now, for the light that is within this cone here, and by the way, this cone is referred to as the numerical aperture, NA, for the fiber, and NA is basically the N0, the refractive index of air or vacuum outside, sine theta 0. And theta 0 is half this angle here, which is determined by then the index difference and so on, to get us to the angle here to be bigger than the critical angle. All right. So then this acceptance angle here, the light within this cone will propagate within the fiber, and when it comes out, essentially comes out just like this cone here, again with an angle of 2 theta 0. So the light coming out from a fiber expands pretty fast. That's using the ray picture. If you look at the true picture, what happens actually, you bring in light that you focus into the core, even though it spills over the core a little bit because of the evanescent wave, then will propagate down the fiber and then will come out on the other side, almost like it came in. So, and this is very close to the diffraction angle, which is of the order of lambda over d, where d is the size as we discussed way early in this course. So even though it propagates as a collimated beam in the fiber, but as soon as it leaves the fiber, it expands very, very rapidly. All right, so that's basically then how, in a simple way, how light propagates. Now, the fact that we have low loss, where does that come from? And let me show you some data on low loss propagation. If you plot the loss in propagation as dBs per kilometer and as a function of wavelength, you find that there is a certain wavelength like 1.55 or 1.3, the loss is very low. It's about, let's say, 0.2% or 0.1% or so per kilometer at these wavelengths. Now, 0.1 dB per kilometer is like 2% per kilometer loss. And that's very small. That's much smaller than propagating in wires. And the reason why it's small is, first of all, is because the total internal reflection is really 100%. All right? There is no loss because of that. And the reason there's any loss at all is because you're squeezed in from one side. On this side, you have what we call Rayleigh scattering. The fact that, I don't want to get into it right now, but the fact that you get scattering essentially from the fluctuations of density fluctuations within the glass. That's on one side. So as the wavelength gets shorter, the scattering gets larger and larger, and then you're in trouble. That's the same reason why the sky is blue and so on. Now on the other side, on this side here, not shown, is essentially the material absorption. Or the infrared absorption and so on for the let's say for the quartz, for the glass. So you're boxed in on one side, you have Rayleigh scattering. The other side going up is the material absorption, and that's why you have the lowest loss around here. And that's about the best you can do. If you want to reduce this loss from, let's say, 0.1 or 0.2 dBs per kilometer, then you have to use other materials. And materials whose material absorption is further into the infrared. So I'm afraid we're not going to get into the visible and have low loss because of the Rayleigh scattering. So it's going to be, if we're going to go we're going to do better than this, we're going to go further into the infrared, which means we have to have the right sources and the components and so on to work in the infrared and then deeper in infrared. Okay, so now we know a little bit about the loss in the fiber, and basically it's very, very low loss if the fiber is constructed very carefully, in the sense that it's synthesized from pure materials and not just any old piece of glass that you find somewhere. Okay, synthesize it from scratch. All right, and it's drawn together, and then you have this core that has slightly higher index than the cladding. So you think everything is fine, but there's a problem, and that's what we want to discuss. Just like with lasers, everybody here wants the lowest order mode, which is the single spot that comes out. But what we find that there are other intensity distributions that come out, and again, these are called the transverse modes that can propagate in a fiber, satisfying Maxwell's equations and so on, and the boundary conditions in a fiber. And this is called, if a fiber is then allows these modes to propagate, then it's called a multimode fiber. Single mode fiber is the fiber that only allows this to go. All the others have high loss and they don't go. So now let's spend a couple of minutes on single mode and multimode fibers before I show you some demonstrations. In this case here, this is the core, and that's the cladding. And the index of the core is N1, which is higher than the index of the cladding, which is N2 down here. Now, on the x-axis here, I'm plotting what we call the V number. What's the V number? Right now, we don't have time to go into any detail, but the V number is essentially a parameter that depends on 1 over the wavelength of the light, on the d sub c, which is the diameter of the core, and the square root of N1 squared, that's N1 being the core index, and N2 is the cladding index. The square root of N1 squared minus N2 squared. Now, it turns out when this V number has a certain value, let's say 2.4 or so on, then you only get, if it's that value or less, then you only get single mode propagation. All the other modes have too much loss, and they don't propagate. So a single mode fiber then is one where the V parameter, which means the size of the core, the wavelength, and the difference in the indices, are such that gives you a V parameter smaller than 2.4, and that's single mode. If let's say you change the wavelength, you make it shorter or so on, V will go up, and then you'll start getting all these multimodes, or just like I showed you before, and then you'll be in trouble. So for some application, not all applications. In this particular case, what I show you is the field distribution and the intensity distribution in the fiber. Here's the core, here's the size of the core, and that's the cladding. And you can see here, depending on the parameters that I choose, some light in this lowest order mode in the field will propagate in the cladding, and so will essentially the intensity. For the next higher order mode, okay, which is similar to the laser cavity modes, the field distribution is something like this, and again, part of it will propagate in the cladding. And when you square it up, if we look at the intensity, it looks like this. That's what these two spots look like that. But the field is really, one is, let's say, positive, the other one is negative. And what you see here is that the size of this higher order mode is bigger than the lowest order mode, and more of it will propagate in the cladding than in the core. So in terms of propagation constant, or how fast they propagate, this one propagates more in the cladding than this one, and since the index is smaller in the cladding than in the core, then this one will go faster than this one. And that's a problem in communications, in using transverse modes. In this next graphic, I show how much, again as a function of V number, but how much of the light propagates in the core and how much propagates in the cladding. So again, for V number below this 2.4 or so, for single mode operation, it turns out that when the V number is very, very small, most of the light, I'm plotting here power in the core, transmitted in the core over the total power propagated through the fiber. Then it turns out when the V number is very small, even the single mode propagates more in the cladding than the core. Okay, because the ratio of P core to P is very small. And as I approach the multi-mode operation, the single mode travels, let's say, about 80% or so in the core, but not in the cladding. Now, when the onset of multi-modes comes about, then the multi-mode will propagate mostly in the cladding first, more in the cladding than in the core, and then as I increase the V number, they again will start coming into the propagating in the core, and their index starts to approach the index of the single mode. But always it's lower than that of the single mode. Okay, so they all travel essentially at different speeds, and also the transverse modes they travel more in the cladding than in the core, as compared with the single mode. Now, to give you an example, for single mode fiber, let's say for a core diameter of 5 microns and a wavelength of 0.8 microns, you need N1 minus N2, the difference in the index, to be 10 to the minus 3. Now, if you want to make the core diameter larger, then you're going to end up with N1 minus N2 even smaller. So it's very tricky to make single mode fibers. Otherwise, you have multi-mode operation. All right. So now that I have talked about single mode and multi-mode fibers, I have two demonstrations for you. One basically shows single mode fiber and coupling into it and what the output looks like, and also we bend the fiber and show that whatever you do is still single mode. It doesn't change on you. All that happens is that you kick light out and you reduce the intensity. But when we come to multi-mode, something else happens. So now first, let's go to the single mode fiber demonstration. In this demonstration, we're going to illustrate the propagation of light in a fiber, a glass fiber. As we know today, optical fibers have a lot of low loss, very low loss, of the order of 1 or 2 dBs per kilometer, and of course they're being used for communication as well as other applications like sensors. So the setup we have is a laser, a helium neon laser over here. Here's the output from the laser. We're going to reflect it by this mirror, and then pass it through a lens. This lens over here focuses the light into the fiber end. And if we can take a close-up of what's going on over here, what you would see is then a lens, this lens then focusing the light in fiber, and the fiber is very close to the lens. And then the rest of the fiber is here. All right? So here is the rest of the fiber. Now this fiber, in fact, what you're seeing over here is essentially the plastic jacket. The fiber core is about 4 microns in diameter, and the cladding is 125 microns. And the rest that you see here is the plastic jacket. That's why it looks so visible, because it's so thick.
The other end of the fiber then goes into this holder, and the chuck here. It's in a fiber holder in a chuck, and the output of the fiber then is over here onto this little screen. Now, if we can, maybe we can take a close look at the fiber end here, which shows that what you see over here. In fact, let me point to it. What you see over here is the cladding. Essentially, we've stripped the jacket, and what you see here is just the cladding, and this is the 125 microns. While over here is the fiber with the plastic jacket. So when you remove the plastic jacket, then you have essentially what you're seeing is just the 125 micron cladding. All right. So this is then the fiber, and there's the output of the fiber. Now, what we see, if we can then enhance this and bring it in, what we see is the single mode behavior of a fiber. And it looks like almost like a Gaussian kind of spot. Not quite Gaussian, but it looks like a Gaussian kind of spot. Now, what I'm doing now is just adjusting the coupling into the fiber. And it's very touchy because, as I said, the core is only about 4 microns. All right, so this is what then a single mode fiber, the output from a single mode fiber looks like. And as I misalign here, it doesn't make any difference. All you get is just a loss in intensity. The shape of the mode stays the same. So remember, the core is 4 microns, cladding is 125, the wavelength of the light is 6328 angstroms, and the core to index difference is about 1 part in 10 to the 3. So this way you can show that indeed you get single mode propagation. Now I would like to illustrate some interesting phenomena about fibers. So if we get the camera to look over here, I want to illustrate how touchy is the propagation of light in a single mode fiber. Now here's a piece of fiber, and you can see that there's no light scattered from the fiber. Now all I have to do is bend the fiber, and you're beginning to see the light that gets transmitted out of the fiber, gets essentially kicked out the fiber, and because of the bend. Now, and the reason for that, because you start going against the rules of propagation of light in a fiber. For example, if you take the ray explanation, is that what you're doing, you are exceeding or you're changing the angle of light with respect to the fiber, which means that if you're below the critical angle, then the light is no longer totally internally reflected and therefore gets kicked out. All right, so here it is. It's very dramatic. As soon as you put a little bend in this fiber, you can kick out a lot of light. In fact, there's the glow right here. Now, if we can bring in the output of the fiber into the inset over here, now you can see that as I increase the bend, all right, you can see that the intensity, yeah, I'll do it even more, intensity then drops quite a bit, which means I've kicked out almost all the light by simply putting a bend into the fiber. So the illustration here then shows that if you leave the fiber alone without sharp bends, everything is fine. If you put in a bend, then you can kick out a lot of light, and then not much will be transmitted. So you have to be careful. You don't put it too tight a bend, otherwise your fiber is brittle and you break the fiber. So you have to be careful how you do this.
In this previous demonstration, then, what we had was a single mode fiber, which means that that's a fiber that satisfied this V number being less than 2.4 or so. And and because of, again, the choice of the core diameter, the wavelength, and the difference in the indices. Now, in this next demonstration, we're going to violate this. We're going to create a V that is bigger than this value here. By in our case, we did it by choosing a fiber that has that's a bigger core diameter. But we could have also done it with by changing the wavelength. And if you just shorten the wavelength, go more into the blue side of the spectrum, then you can you start to see transverse modes like I showed you before. Okay, and I think now we're ready to have fun with a multimode fiber. Now we've replaced the previous fiber with another one. The only difference between this fiber and the previous one is that the core diameter is now a little bit bigger. It's about 6 microns instead of 4 microns in the previous fiber. Setup is exactly the same. Again, we have the laser here getting reflected by this mirror and this mirror into the lens, into this fiber, this new fiber, and then the output of the fiber goes onto the screen. So let's now take a look at the output of this fiber. So what first thing we see, that doesn't look like a single mode at all, that single lobe. And if I change the adjustment, if we can have the camera looking at my adjustments, then you see that I can get a variety of shapes. All I'm doing is changing the adjustment. And I can get a variety of shapes, and clearly it's not like what we had before, the single mode behavior that we had before. And this is then the so-called multimode. What you're seeing are different transverse modes that can propagate in this fiber because the core diameter is bigger. But I'm going to leave it to you then to explain why. Exactly why you get higher transverse modes propagated in this fiber. Again, the wavelength is the same. The only difference is that the core diameter is bigger. You can see this one here. You get a nice dark line in the middle, and then if I align it over here, you can see it's blobby. It's a mixture of modes. That's why you don't see sharp dark line in the middle, but you get a mixture of modes. While remember in the other one, no matter what I did in the alignment, it was still single mode coming out, just one lobe coming out. All right, now multimode fibers have many applications also, but for today, for a lot of sophisticated sensor applications and communications, one generally uses single mode fibers. So here's a pretty mode with a dark line down the middle. Now what I would like to do is show how touchy this fiber is to bending. In fact, if we take a look at the fiber here, as soon as I just press on it, if we take a close look at it, if I just press on it, I can kick light out. If I just simply press on it, I can kick some light out. So it's very touchy to stress and to bend. What I would like to do then is show that I can kick out some of the transverse modes by simply bending or stressing the fiber. What I'm going to do is then bend this fiber, and if you watch in the inset, you can see that the intensity will go down, but if I keep increasing the bend, I end up with a single mode propagation, but weak. And this illustrates that you can strip off the high order modes by simply bending the fiber. But the penalty is you get much less light getting propagated. So here we have single mode propagation, and here we have multimode or mixture of multimodes that are propagating in the fiber. Again, you can see that there's a lot of light that gets kicked out, has to be kicked out of the fiber. You can see the bend absolutely glows. In fact, this bending
effect on the transmission of light in a fiber can be used as a sensor. A sensor of pressure, sensor of stress, bends, and what have you. All right, so then in summary, we've looked.
Well, that was all about transverse modes in fibers. It's not easy to see these modes in normal fibers, but I think this was a nice opportunity for you to see them and how they get manipulated. So what we know now about fibers then is that there's low loss because the material is correct. We go to, let's say, the right wavelength, and we have the, let's say, lowest loss, if you need the lowest loss. For a lot of other applications, like sensors and so on, you know, the fact that the low loss is not the most critical factor. But certainly for communications and long-distance propagation, that is very critical. And then we also learned that we have to be careful with this V number so that we make sure that we have, let's say, when we need it, we have single-mode propagation. See, the problem with these multi-modes, they travel at different speeds, and then, as we showed, and then it prevents you from using these fibers for wideband communication. So for wideband communication, you really need the single mode. And also what's nice about propagating it around 1.5 microns or so is that even the refractive index, the variations in there is also small. So it's a nice region to propagate for communication applications. But just fibers alone is not everything. You still have to make connections. You know, like couplers, you have to have other components, and so on. So let's now spend a few minutes on fiber optic components, like couplers, because if you want to split the light by 50-50 or 80-20 or so on, you need these directional couplers, all done with fibers. You need polarizers, because you don't want to come out of the fiber, go through a bulk optic polarizer, and go back into the fiber again. You'd like to create polarizers right on the fibers. You'd like to also control polarization. You'd like to maybe create phase modulators, frequency shifter, and so on, all in fibers. Now, I'm not going to have time to talk about all these things, but I'm just going to talk a little bit about couplers, maybe a little bit about phase modulators. So how do we make a coupler? Or how do we transfer light? Let's say we have a fiber in here, and we have a core in it, and we're propagating down the core. And normally the light would come out here. But now I'd like to transfer the light to another fiber. So what one does here, you bring another fiber close to this one. Now, if with fibers, as we said before, they have a core and they have a cladding, and the cladding is usually much bigger than the core. The core is usually a few microns. The cladding, as I mentioned in the demo, is about 125 microns. So if you bring that close to this one, then the two cladding spacing will not let you transfer any light from one fiber to the other. So in order to transfer light, what you have to do, take advantage of this evanescent wave, the part of the evanescent wave that's traveling in the cladding. So what you have to do then, you have to shave off the cladding so that that evanescent wave in this fiber here, fiber 1, okay, if you shave enough of the cladding, this evanescent wave can start propagating in the second fiber, in fiber 2. So when it does that, then you can transfer energy to fiber 2. And depending on this interaction length of the interaction, the closeness of the two cores, then you can transfer 100% and back to 0. So in this plot here, we show that as a function of either the separation between the cores, D subcores, the core separation, or as a function of the interaction length for a given core separation, you can transfer as much as 100% of the light. You can make 100% of the light come out at port 2 instead of port 1. And if you keep changing this coupling, then you can bring it back to 0 again and up again and so on. So that by selecting the right separation between the cores and the right interaction length, then you can transfer any amount of light that you want. And this is great because it's pretty low loss and is used, of course, all the time today. These couplers can be what we call the polished type or the fused type and so on. There are different types of couplers, but basically they work on that principle of bringing the two cores close enough together so that the evanescent wave, that little tail of that field distribution, then will propagate in the other core and will drive the dipoles over there. All right. So that's basically the principle of a coupler. All right. And now I wanted to just say again a few words about phase modulators. Now, phase modulators. Well, how do you do that? How do you modulate the phase of the light propagating in the fiber? Well, again, there are many ways, because if we stretch the fiber, if we do something to the fiber, we can change essentially the index, let's say, in the fiber, or change the physical length of the fiber, and then we get a change in phase, delta phi, that's proportional to either change in the length of the fiber or change in the index of the fiber. One way of doing this is to take the fiber and wrap it around a piezoelectric crystal. If we put a voltage between the inside and the outer surfaces of this crystal, then we can change the diameter of this cylinder, and then in this way we can change the physical length of the fiber, or by stressing it, essentially could change also the index. But whatever, yet you get a change in the phase of the light propagating by applying a voltage, either a DC voltage or sinusoidal voltage, to this cylinder, piezoelectric cylinder. Another type of piezoelectric device is a sheet. Is a piezoelectric strip or sheet where the fiber is just attached to, bonded to this. You don't have to bond it that rigidly to this sheet. And then by applying a voltage between the upper and the lower surface, you can again stretch the fiber, and then you can essentially modulate the light that's propagating. So that's a very neat way. You don't have to break the fiber; it's still intact, and you can get phase modulation. Now, and then as I said before, there are all kinds of neat devices that use fibers. So you can make polarizers, frequency shifters, and so on. But now there is another field that is gaining momentum a lot, and that's called integrated optics. Because sometimes to make these all fiber couplers, all fiber devices, becomes a little tricky and very delicate. So it would be nice to replace them with something that's more robust. So I'd like to talk a little bit about integrated optic components. And what are integrated optics, first of all? Let me then explain to you a little bit about what's an integrated optic waveguide is. So in this case, it's not a fiber, but basically, let's say you start with some material like glass, and then you indiffuse some impurity that raises the index. And if this is controlled, then using photolithographic techniques and so on, that you can raise the index over here. So if you look from the side, you have a material that has a little higher index than the cladding over here, and then you can propagate light down this waveguide. It becomes a waveguide, and you can, and then the light is guided through the waveguide, just like in a fiber, because the index here is higher than one's on the side. And then you can coat this and protect it and so on. But the principle is that you can get single mode or multimode waveguides in a substrate, and it's rigid, doesn't go anywhere, and you can do all kinds of things with it. So now with this idea here, you can create a directional coupler, either fixed or variable. Again, you can create polarizer by preventing certain polarizations, or one polarization from going by attenuating it. You can create phase modulators, frequency shifters, intensity modulators, and so on, all using integrated optics. So let's look at an example. Here again is the substrate, and here's the waveguide. Now, if this material here is before even I get to what I want to talk about, is that you have to first couple coupled to this waveguide. Remember, the core can be very small, just a few microns. So you have to take the output from the fiber and couple it into this core. So that's a tricky device, but again, people have found nice techniques to do that. So basically, you want a fiber to couple into this and this to couple into the fiber going out. If you can do that and these couplers stay together, then you've got something. All right. So now, how do you create a phase modulator here? Now, if this material is, for example, is slightly electro-optic, then by putting electrodes here and applying a voltage difference between them, then you can change the index, either in the cladding or in the core, and then just by simply applying a voltage. And this way, you can then phase modulate the light propagating in this section. You can do it pretty fast, and then you can get very fast phase modulators. And if you ramp the phase and so on using Ceradyne techniques that we hear about today, you can also do frequency shifting quite easily using this device. Now, if you want to use it as a coupler or as an intensity modulator and so on, you have to combine several waveguides, two waveguides together, and then you can create a coupler and so on. But here I've chosen this example here where I have one guy that looks like this and then the other guy that looks like that. Now, if I put light in one arm, then again, normally it would come out on over here, but depending on the closeness of these two cores, then I can get some light that will be coupled into this other side, will come out over here. So this is let's say a fixed coupler. If you want to have a variable coupler, again, if this material of the substrate is electro-optic, then again putting electrodes on the material, then you can change essentially the index here between the cores, and this way will change the coupling. The coupling ratio then will change depending on the index. So I can couple more light or less light by applying a voltage. So this is a neat little device. And then there's also other applications. You can also use it for example, as a intensity modulator by again applying a variable voltage here, and then you can vary the transfer of light from here from this port to this port and so on. So it has many applications, sensors and so on. So this is a very important field in fiber optics, as long as you know how to couple back into fibers and in a rigid way without any reflections or big reflections and so on. So it's a very exciting development. Now, what I'd like to do is talk a little bit about fibers for sensors, special fibers for sensors. So far, the fibers I've talked about are good for communication. Okay, single mode fibers, low loss, and so on. But for sensors, there are all kinds of fibers that have been developed. And it's a field that is growing. It's a little difficult to get started, but it is growing. Now, today we have what we call polarization maintaining fibers. These are fibers that will, if you launch the field at one polarization, will stay in that polarization. There are fibers that will only propagate one polarization. The other polarization will not propagate. It's too much loss. And so you have essentially like a very long polarizer, linear polarizer. Then we get to what we call coated fibers. These are fibers that are coated with special materials that if they are placed in a certain environment, then that material will start stretching and will stretch the fiber with it, and then you can make a sensor for that particular species that the fiber is dipped into. You can also get other types of coatings. You can coat the material with a conducting material like copper or so on. You can make it more sensitive to temperature. You can coat the fiber with piezoelectric material, and you can make it into a phase modulator or magnetostrictive material, and so on. You can put all kinds of coatings on fibers and use them for sensors. And the jacketed fiber is almost like the fiber. You put it with a jacket, and then you make the jacket sensitive to, just like I mentioned before, to the species that the fiber is dipped into. Then today it's a big field now, the doping of fibers. And for example, if you dope glass fiber with neodymium, you have, and you can pump it with a laser, with a semiconductor laser, then you can have essentially a neodymium laser, a fiber laser. And you can make them into linear lasers or ring lasers and so on today by doping the fiber. And this is the background for the fiber optic lasers, because you dope the fiber with all kinds of impurities, and then you have to pump them, and then usually these are pumped with a semiconductor laser or some other laser, and then you can create all sorts of lasers. So you've got to watch this field now. It's going to be very big. Then there's another type of fiber where you expose the cladding. You shave off the cladding, expose the core. All right. So by exposing the core means that you're exposing the evanescent wave that I've talked about before, and that can be used. That tail of the evanescent wave can be used to interact with vapor or gas or liquid or whatever that is placed in, and you can use that as a chemical sensor. And then we have twin core fibers where the two cores are close, and then you can transfer light from one core to the other all the way down the fiber, and this can be used for temperature, stress, and so on. As I say, this is a huge field, and I think we need a whole one-day course on fibers. So now I'm getting close to the end, and I hope I've got some ideas across about the basics of fibers without using math, without scaring you off. But obviously, if you have interest in these things, you have to consult the literature or take other courses. In the few minutes remaining, I would like to talk about just a few words about some future developments, both in lasers and fiber optics. In terms of lasers, certainly we're going to see the rise, and we're already seeing the rise of semiconductor lasers, for all sorts of applications, CDs and so on. But we're going to see them replacing the red helium neon laser. Today they're already available, and in fact you see them as pointers and so on. And so they're very neat little devices, and for applications that don't require strict wavelength stability and what have you, I mean, these are great lasers. We're also seeing, and we'll see much more, semiconductor lasers that are used to pump solid-state lasers, and fiber lasers, waveguide lasers, and so on. And this is a very nice application for semiconductor lasers because, again, you don't have to worry about the stability of wavelength and so on. And then they can pump very well-behaved solid-state lasers. And today these can be also very big. They don't have to be very small. They can be very big, and you have an array of semiconductor lasers that will pump them. And then we go from the big to the small. We have even microchip lasers. They're very tiny crystals, and then they are pumped again with, let's say, semiconductor lasers or other lasers. But they're very tiny, and they can be single frequency and tunable and so on. And the fiber optic lasers, well, we already mentioned there are all sorts of materials being looked at and pumping sources. And then the thin film waveguides. Well, we talked about waveguides. All you have to do is you dope that waveguide, pump it with an optical pump, and then you've got yourself a laser in that substrate. And then vacuum ultraviolet lasers are very important in medical applications and other applications, and we're seeing lots of new developments in here, and also X-ray lasers. In the early stages, they classified their development, but now I think the literature now we see all kinds of work going on in X-ray lasers with, again, completely exciting area of applications for X-ray lasers. Now this is the lasers. Now in terms of applications, I mentioned before, fiber optic communication. That's a huge application, and we're going to see, I think, not that far, we're going to see that their homes and all that will be linked with fiber optic cables. And this way we can have huge bandwidth that's going to be transmitted in these fibers, and then we can send all kinds of information all over the place. There's areas of materials processing, again because of the availability of a variety of lasers. That certainly is increasing, and the variety is also increasing. And medical procedures is, if you keep up with what's going on, it's incredible what the lasers are being used for procedures and for diagnostics and so on. Now here's a tough area, data processing. Lasers are being used, but hopefully it will increase more. You can take very fast Fourier transforms, optical techniques, but again, you have the implementation of them is not that easy. Now sensors, I've already mentioned some words about sensors, but not just fiber optic sensors, but all kinds of optical sensors. They are incredible devices in the sense that they're not affected by, especially the fiber optic sensors, they're not affected by electromagnetic interference, and they can be used in all sorts of hostile kind of environments that normal electrical sensors would not work at all, because they will be affected by the electromagnetic interference. Also because fiber optics fibers have low loss, you can have all kinds of distributed sensors and so on, because the fiber, as I say, doesn't have any loss, so you can place sort of sensors all over the place and collect data from a large area. Now, I mentioned earlier precision positioning. This is based on interferometry, laser interferometry. Using laser interferometry, you can monitor the positions of workpieces and so on, and dimensions and sizes and movements of all kinds of things, and you can put them in feedback loops, and they improve things for you. Then laser shows, I don't know, I don't keep up with laser shows, but every time I see them, they always fascinate me, because I'm always curious about what kind of lasers they're using. And today they can use them to write all kinds of patterns and messages and so on for people. Then there's the computer interconnects. These are the fiber optics or integrated optics that are being used for connecting computers or even connecting boards. And hopefully sometime in the near future we will see all optical computers. Now these will be very fast, based on these mode-locked very short pulses, and but there are a lot of challenges, and hopefully some of these challenges will be overcome. Then in terms of high-density memories, well, we're already seeing that now, but hopefully there will even be even more dense, taking advantage of three-dimensional structures and so on. And finally, I'd love to see some color holography becoming popular, so that we can have all sorts of color holograms around our workplaces, around our homes, and so on. So far there's all kinds of holography available, but the true color holography, even though it is feasible, we haven't seen them, at least that available, so that one can purchase them and put them up on the wall. I see that my time is close to coming up to an end, and I hope that I've been able to get some ideas across to you, again, without scaring you off. Certainly I hope that for those of you who didn't have too much background, I hope you have motivated you, take some interest in lasers, in fiber optics, and maybe you can find some new applications for them, because the field is very young, and it needs some more energetic people that will come in, and especially from different fields. It's not always, one shouldn't always talk to people in the optics and laser field. One should be talking to others in other fields. Maybe they'll recognize some new applications. As we can see, there are really so many applications of lasers and fiber optics. Now, before I close, I'd like to thank two of my graduate students, Steve Smith and Farhad Zarinechi. I have put them in a circle here because it's difficult to choose between them. Although Farhad Zarinechi has now graduated, Steve Smith is going to be graduating soon, and they've helped considerably in the creation of the demonstrations, and also in the creation of these visuals. I hope that you found them readable and without a strain. So I think I'm almost dead on time, and I'd like to thank you for listening. And if you have any questions or so on, I think you have our phone numbers here at MIT, and you can call and we can continue with this conversation. Goodbye for now.